Alrighty, welcome back to some more fun maths. Today we're going to be looking at independent events. So again, this all relates to probability topic that we've been studying. So they're just giving a bit of background information here and thinking about whether something is independent or not. And so they've said here, hey, let's think about if you were to toss two coins and to work out the probability that the second toss is a head, given that the first toss is a head when you're tossing that coin twice. So they're saying, hey, let's define A as the event of the second toss and B as the event of the first toss of the head. And so really, when you're finding out the probability of the second toss being a head, given that the first toss is a head, you're really working out the probability of A given B. Remember that symbol there is given. So finding out the probability of A given B is what we're going to be working with. There was a conditional probability definition that we learnt the other day, which says that the probability of A given B is equal to the probability of A intersection B divided by the probability of B, the thing that's given. Cool. So in this particular case, if we're thinking about these two events, A and B, the first and the second toss of the heads, the fact that you're looking at A intersection B is when they are both heads. So that's on the top, and then we're obviously it's going to be divided by probability of event B, which we're saying was the first toss being a head. Now, if you work out the probability of both of these, probability that both tosses are heads is a quarter, or 1 in 4, and then that's going to be divided by the probability that the first toss shows a head. Again, the probability of the first toss being a head is a half. If you have a quarter and you divide that by half, it's really the same as a quarter multiplied by 2 over 1, which is 1/2. Now, as it turns out, you'll see that the probability of that second toss showing a head doesn't really affect the outcome of the first toss, and therefore they are independent events. What you do need to note is this bubble box here, which says that if two events A and B are independent, they are independent because the occurrence of one event has no effect on the probability of the occurrence of the other event. So if you do have a scenario like we just spoke about where you've got the probability of A given B and it's just the probability of A, and so it doesn't really interfere or with the other one, it has no effect, then these events are said to be independent. You can take that a little bit further, and we can also get a further rule for independence. It says here, if events A and B are independent, they are independent if this rule is true here. So it says if A intersection B is the same as the probability of A multiplied by probability of B, when both of these are the same, then we can say that events A and B are independent and have no effect on each other. Cool. So let's actually have a look at an example that will talk about that. Oh, cool. We've got 500 people. They've questioned, they've been asked questions, so they've been bundled up and asked some questions. And we've got the category of how old they were. So the question they were asked was whether or not they use social media regularly. And you can see the results here in this particular table. Whether they were less than 25, we got some responses either yes or no, and if they were greater than or equal to 25, so 25 or above, their response is yes and no there. You can see here the total was 500, which is in the corner here. And we've got the tallies of the totals both ways as well. So the total for the age less than 25, there were 240 people, and there were 260 that were 25 or above. 300 answered yes, and 200 answered no. So here it says, is the regular use of social media independent of the respondent's age? So seeing if they affect each other. So what we can do is, first of all, we're going to find out what the probability of their age being less than 25 intersecting with yes. So in this particular case, probability of being less than 25, intersection yes, that's this response here. I should really draw that on there. That's probability of age 25, and yes, it's 200 out of the 500 respondents there. So that simplifies down to 0.4. Cool. Now, if they are independent to each other based on the rule, the intersection of those two should be the same as the probability of one of the events multiplied by the probability of the other event. So let's see. First of all, we've got the probability of being age 25. We're going to multiply that by the probability of yes. So probability of age being less than 25. Here you've got age less than 25 was 240 out of the 500 respondents. Is the probability that their age was less than 25. If we think about the probability of them saying yes, for them to say yes, there was 300 out of the 500 that said yes. If we simplify down each of those fractions, we end up with 0.48, and here we end up with 0.6, and we are going to multiply those together, which is 0.288. Now, as we set up here, if they were equal to each other, the intersection of them was equal to the probability of each of them multiplied by each other being the same, then they were independent. In this particular case, it turns out the intersection, which was 0.4, isn't equal to the probability of each of those events, which was 0.288, so therefore they are not independent. Worked example number 26. Oh, cool. It's an experiment drawing numbers at random. Excellent. So you got the numbers 1 through to 8 as the possibilities. They're saying let's set A be the numbers 1, 2, 3, and 4, B being 1, 3, 5, and 7, and set C being 4, 6, and 8. Cool. They're asking us now to just run some tests to see whether certain sets are independent of each other. First things first, we just noted what the probability of getting A is, what the probability of getting B is, and probability of getting C is. Again, here, probability of getting A is a half, which is really because there are 4 possibilities out of the 8, which simplifies down to the half. Here, again, there was another 4 out of the 8 in total, which simplifies down to a half. And probability of getting a C, there were 3 out of the 8. Okay, so that's how we got each of those probabilities there. So first of all, let's work out here, are A and B independent? Okay, so first we need to find out what the probability of A intersection B is. So the probability of A intersection B, these are the things that overlap that are in both A and B. Yep. So here if we look at A and B, the sets A and B, the numbers 1 and 3 are in both of those. So in that particular case, again, you've got 2 numbers out of the 8, which simplifies down to the 1/4. Okay, so that's what A intersection B is. From there, we're going to see if they are independent. We're now going to do probability of A multiplied by probability of B, and we'll see if they are the same. If they are the same, then it'll be independent. So up here we had the probability of A was a half, probability of B was a half. Multiplying those together, we get it's equal to a quarter. The good news is, in this particular case, the probability of A intersection B is the same as the probability of A multiplied by the probability of B, and because they are the same, we can say that they are independent of each other. Cool. Let's do the same this time with A and C. So first of all, we'll find A intersection C. So the numbers that are in both of these sets here, it's just 4. That's in both of them. So in this particular case, it's just 1 number out of the 8 that is in both of them. Let's now find out the probability of A and the probability of C, and we'll multiply those together. So half multiplied by 3/8, that's 3/16. For them to be independent, the probability of A intersection C should be the same as the probability of A multiplied by the probability of C. In this particular case, they are not equal to each other. Because they are not equal to each other, they are not independent. Last but not least, we've got are B and C independent? Again, let's see what B intersection C is. There are no items that are in both B and in C, so that's a null set there. So that's 0. Obviously, let's find out the probability of B multiplied by the probability of C. That's going to be a half multiplied by 3/8. Again, that's 3/16. It turns out in this case, the probability of B intersection C is not equal to the probability of B times probability of C. Because they are not equal to each other, again, they are not independent. Cool. Going a bit further, it says here, the concept of mathematical independence is sometimes confused with that of physical independence. And what they're going on to talk about is if you've got two events and they are physically independent in the real world, then they are also mathematically independent. But the other way around is not necessarily true. And so this example is trying to illustrate that. So we've got worked example number 27 here. Happy days, it's rolling a dice again. It says if we roll a dice twice, these are the events that we're going to get. They're saying event A is the first roll, shows a 4. So on one of the first time we roll the die. The second time we roll the die, we're going to call that event B, and it shows a 4. Event C is the sum of the numbers showing at least a 10. So roll 1 and roll 2, when we add those together, it's 10 or more. So it says here, first of all, asking are events A and B independent events? So here's how you'd go about proving this. It says here, since A and B are physically independent, so you're rolling the dice physically twice, they also must be mathematically independent. But we can check this mathematically. So again, if you have the probability of A multiplied by the probability of B. If we think about the probability of A, the first roll shows a 4. The probability of that's going to be 1 out of the 6 numbers that are on the dice. So it's 1 in 6 is the probability of rolling a 4 first. Probability of rolling a 4 second is again 1 out of the 6 numbers on the die. If we multiply those together, we get 1/36. So that's the probability of A multiplied by the probability of B. If we then went on and we wanted to work out the probability of A intersection B, what you should consider is, it says here, if we write the sample space as ordered pairs, so the first entry is the first throw of the die, second is the second throw of the die, so they're listing out all the possibilities here. You could roll a 1 first, and then a 1, or 1, then a 2. Maths people, we get a bit lazy, so we just put ... Here are all the other possibilities, up to rolling a 6 and a 6. Yep, so we know you could write them all out. This is saying the number of all of the possibilities in the sample space is 36. Yep. So the event A intersection B corresponds to the outcome where you've got it says here the first roll is a 4 and the second roll is a 4. So again, that would be the ordered pair 4 then a 4. In that particular case, the number of ways in which you can get A intersection B is 1. There's only one way out of all of these that you can get a 1 first and then a 1 second. So again, if you are thinking about this, the probability of A intersection B is 1 out of the 36 possibilities that there were. Because the probability of A intersection B is the same as the probability of A multiplied by the probability of B, it's also 1/36. They are the same, so therefore we can say that A and B are independent. Next one says, what about A and C? It's really saying, is A and C independent? So again, C has to add together to show at least 10. So here are the ordered pairs of the combinations that you could get 10 or above, 4 and 6, 5 and 5, so forth and so forth. Rolling a dice first and then rolling a dice second, there are 6 different ways in which you can roll a 10 or above. So again, to work out what the probability of A multiplied by the probability of C is, before we worked out what the probability of A was, it's 1 in 6. The probability of obtaining a C, there were 6 possibilities out of the 36. Running this calculation, again we get 1/36. If we then go and work out the probability of A intersection C, A intersection C is where it corresponds to the outcome of 4 first. So A was rolling a 4, and the only other combination there with that one that's going to work where it's 10 or above is a 4 and a 6 there. Okay, so there's only one way to get that. So in this particular case, probability of A intersection C is 1/36, which is the same as the probability of A multiplied by the probability of C. Because they are the same, we can say that they are also independent events. Cool. One last example. It says knowing that events are independent means that we can determine the probability of their intersection by multiplying together their individual probabilities, and it says this is illustrated in the following example. So this is worked example number 28. It says, suppose that the probability that a family is in a certain town owns a television, and they're denoting that as T, and they're saying it's 0.75. Cool. It says the probability that the family owns a station wagon, so a car, is S. It's a certain type of car, is 0.25. Perfect. It's then saying if these events are independent, so it's actually telling you that they are independent. And because it's telling you that they are independent, we can use the knowledge that we've got there to work out some of these probabilities. So part A is saying, hey, a family is chosen at random, or what is the probability that a family is chosen at random and that they own both a television set and a station wagon? Cool. So in this particular case, for them to own both a television and a station wagon, where you've got the word "and" there, it's television intersection station wagon, T intersection S. We know that T intersection S, if they are independent, is the same as the probability of television, T, multiplied by the probability of station wagon, S. Yep. So because they've said that they are independent, we can run this calculation based on this rule. So probability of T was 0.75 multiplied by the probability of station wagon, which was 0.25. It's 0.1875. Perfect. Last but not least, it says here a family chosen at, what's the probability that a family chosen at random owns at least one of these items? So again, if we think about at least one of these owns at least one of these items, it means either they own a television, or the union, or they own a station wagon. Yep, so T union S is what we're looking for in this particular case. From some of the previous lessons, T union S is the same as the probability of T plus the probability of S take away the probability of T intersection S. And that's the addition rule that we've spoken about before. From the previous example, or part of the question, we worked out what the probability of T intersection S is. So we can run this calculation. Probability of T was 0.75, probability of S was 0.25. Take away the probability of T intersection S, which we worked out up here, which was 0.1875. We can run that calculation, we get 0.8125. Thank you very much for listening. There's a fair amount of information that we did get there. Bye for now.